All right. So hello, everyone. My name is Michael Omatsola-Morgan, and today I'll be talking about my research project, which is investigating industrial hemp biomass as an alternative fuel in diesel engines. So this is a collaborative project between the Bioenergy Group in the Department of Chemical Engineering and the Future Engines and Fuels Laboratory in the Department of Mechanical Engineering, both at the University of Birmingham. So today I'll be going over the following. I'll first provide some background and context as to why this research is so important. I'll then talk about some literature review, talking about the current conventional method of making biodiesel and this new cutting edge technology that I'll be proposing to use. I'll then talk about my project aims and briefly give an overview of what I'll be doing throughout the research. I'll then talk about the history of hemp or cannabis. I'll then talk about government regulations that surround the cultivation of cannabis, and then some current legal cases that are forming against government policy. And then finally, I'll finally link it back to a local case study, local to Birmingham, as to why this research will be beneficial. And then I'll provide some concluding remarks, and the remaining time will be left for questions at the end. So the climate crisis continues to impose a significant threat on key natural and human systems. Wildfires across the globe are occurring more frequently and with increasing catastrophic impact. So the scientific consensus is that most of the observed warming over the last 50 years is likely to have been influenced by human activity. So it's no coincidence that there's a positive correlation between human population and global carbon emissions as well. Now, if humans continue to disregard calls to protect, preserve, and replenish our environment, the global population will face radical consequences. So in 2019, the UK government announced its plans to bring greenhouse gas emissions to net zero by 2050. A full fact article has analysed the claims made by the government, and they came to the conclusion that a few other countries have set similar or more ambitious targets. Furthermore, they've concluded that while the UK has exceeded in cutting its own emission targets and have made bigger cuts compared to other G7 countries, this isn't enough to meet the future reduction targets. This was analysed using the current environmental policies that have been made. So it's really important that the UK implement more policies that ensure that this reduction target is met. And the Prime Minister has announced the creation of the Jet Zero Council, which are being tasked with making net zero emissions possible for future flights. And furthermore, they've pledged £350 million to fuel a green recovery and cut emissions in heavy emitting industries. So the transport sector accounted for 24% of emissions in 2019. Transport is currently the largest emitting sector of UK greenhouse gas emissions. And looking more specifically at road transport consumed more than 50% of the oil demand in 2019. So this graph shows between 2001 and 2018, the number of diesel-fueled vehicles that were on UK roads. And between this time period, we've seen the UK has seen a steady increase in the number of diesel-fueled vehicles. This graph shows in the same time period the number of diesel imports that the UK have purchased, and over the time period, we've seen that the amount of imports have been increasing. So it's fair to say that the UK has increased their dependency on diesel. Now, the UK plan to rely on these diesel imports for the foreseeable future, but they have an interest in diversifying their road transport methods to electric and ultra-low emissions vehicles, or ULEVs. So ULEVs are vehicles that emit less than 75 grams per kilometre of carbon dioxide from the tailpipe. In 2019, they accounted for 2.7% of all new registrations, and hybrids being 53% of these registrations. But there's global potential for ULEVs. It's estimated that by 2030, there will be a global market worth of £2 trillion. And now biodiesel is something that would go hand in hand with ULEVs, specifically hybrids, because they're more sustainable and they also provide a domestic renewable energy source. So this graph shows the proportion of diesel and biopetrol that's come from a renewable and sustainable source. And we can see that throughout this decade, the use of biodiesel has been fluctuating, but it only accounts for a minority of diesel that's being consumed. This graph also shows a more quarterly breakdown to give you the more recent information. And we can see that there's now an upwards trend with biodiesel, which is a good thing to see. However, biodiesel has been a subject of research for many years now. So why does it only account for less than 7% of the fuel that's being consumed? Well, it depends on three things. It depends on the feedstock that you're using, depends on the conversion process, and it also depends on the fuel quality. So starting with the feedstock, I'll be blunt. Hemp is cannabis with a low THC content, so it's non-psychoactive. But industrial hemp has some fascinating qualities that make it an ideal candidate to be a domestic renewable energy source. So it's a fast-growing biomass and produces high biomass yields. It's also a very eco-friendly crop as well, so it's an excellent carbon sink. It can sequester more carbon dioxide per hectare than what woodlands can sequester in the same year. It can also readily remove heavy metals from contaminated soil through photoremediation. And because it has a long rooted system, this can cover more volume of soil, therefore being more susceptible to photoremediation. Actually, in 1998, after the Chernobyl nuclear disaster, Ukraine's Institute of Bass Crops exclusively planted hemp crops around the surrounding area to study its soil restoration abilities. Hemp is also a natural insecticide, herbicide, and pesticide. Therefore, it eliminates the need for agrochemicals, and therefore fewer inputs are needed compared with other crops. Something that I find fascinating about hemp is how its different byproducts can be used for many different applications. So the leaves and flowers have therapeutic benefits. They can be used in medicinal preparations or even as animal bedding or compost. The seeds are both high in protein, which can be used for food, but they can also be pressed for their oil. And this can be used for cooking oil, cosmetics, biofuels, bioplastics, and even printer ink as well. Just to point out, the hemp seed oil, it's high in polyunsaturated fatty acids, and I'll talk in the next slide as to why this is useful in a biofuels application. So then next we have the stalk, which can be broken down to its fiber, which can be used for textiles, insulation material, and rope. And then the herds, which can be used for paper, compost, bedding, and fiberboards as well. And then lastly, we have the roots as well, which can be used for medicine and organic compost as well. So moving on to biodiesel production, the current conventional method of making biodiesel is transesterification. So this process involves converting vegetable oils, which is just a mixture of triglycerides, this molecule here, into biodiesel, which is a mixture of fatty acid methyl esters. So this process is cheap and easy to mass produce. And the fuels that you get, they have these two oxygen atoms within the chain. So they actually promote cleaner combustion when they're combusted. But then this is traded off with having a lower energy content. So what that means is more volume of methyl esters is needed to achieve the same power output compared with fossil diesel. And this ties in with the third quality that I spoke about, the fuel quality of the fuel itself. So taking the example of hemp seed oil, depending on what fatty acid content is within the vegetable oil gives certain properties to the biofuel. Because it has a high polyunsaturated fatty acid content, which to explain it is just a chain that has more than one carbon double bond, it's actually more susceptible to oxidation, and this isn't good for an engine. I'll turn on my video and I'll show you this. So this is an engine that's had hemp seed fatty acid methyl esters just lying around in it. And now you can actually see that this shaft is a bit darker than the actual casing. So what's happened is the fuel's oxidized and now the engine is stuck. So it's actually bad for an engine to, for a fuel to oxidize within an engine, because it can also damage the engine with the with the deposits that the fuel creates. So what you can do is you can use a process called selective hydrogenation to remove the polyunsaturated fatty acids and convert it just to unsaturated fatty acid. And this is beneficial because this methyl ester, methyl linolenate, oxidizes at a rate 100 times faster than methyl oleate, and methyl linoleate oxidizes at a rate 40 times faster than methyl oleate. So by decreasing the content of these two methyl esters, you therefore increase the oxidation stability. It's also worth noting that these hydrogenated fatty acid methyl esters can be used in aviation engines as well for biokerosene. So there's a wide range of applications that these fuels have. Now these methyl esters need to conform to the standard EN 14214, which basically gives you the requirements and the test methods for methyl esters that can be used in diesel engines. And then this biodiesel can blend with other biodiesels and also fossil diesel as well. So now I'll talk about thermo-catalytic reforming. This is a new cutting-edge technology of converting biomass and other waste products into biofuels. So we'll watch this video and then I'll speak in the next slide more about the process.
Birmingham's Energy Institute in the University of Birmingham is working in close partnership with the Fraunhofer in Germany to deliver the new thermo-catalytic reforming technology to market.
This technology converts all types of residual biomass and plastic wastes arising from households, agriculture and industry into easily storable and transportable biofuels for vehicles and combined heat and power applications.
Renewable energy technologies are becoming increasingly important in these times of climate change, and the Fraunhofer Institute has developed a new process based on the efficient use of biogenic residues. TCR, or thermo-catalytic reforming, benefits from high feedstock flexibility and can take a range of problematic organic wastes, including animal manure, agricultural residues, straw and husk, food waste, organic waste, sewage sludge, municipal solid waste, and biogas digestate. The TCR technology site is at Tyseley in Birmingham. Various biomasses and biomass residues can be transported into the site by lorry or barge. They are unloaded and used as feedstock for the TCR technology. The TCR converts the biomass residues into gas phase, liquid phase and char, all of which are of unique quality. The char can be used for co-firing in power plants and also in agriculture as fertilizer. After refinery, the fuel we produce can be used in cars, both petrol and diesel engines, and even as jet fuel for the aviation industry. Finally, in the gas phase, the hydrogen can be used to create electricity in combined heat and power plants, as well as being used in hydrogen fuel cells and as fuel for cars and trains.
Today is a significant day as it marks the delivery of our first demonstrator to the City of Birmingham at Tyseley Energy Park.
The Energy Park will combine all types of new and existing renewable energy technology to produce green fuels for the City of Birmingham.
The Energy Park is one of a number of energy innovation zones within the Energy Capital, a new vision that aims at making the West Midlands one of the world's leading destinations for energy innovation and investment.
Phase 1 of the Energy Park has seen the delivery of a 10 megawatt wood gasifier, and this reactor will be linked to the second phase of development on the low carbon refueling station.
Our thermo-catalytic reforming technology is not only part of the Energy Park, but is also part of the Birmingham Thermal Belt, which is a concept first coined by Professor Andreas Honan in 2008 to realize 20 decentralized biomass conversion plants around the cities.
This particular reactor, which you can see behind me, will convert up to 80 kilograms an hour of biomass and plastic residues into bio-oil, hydrogen-rich synthesis gas and biochar for energy generation and value-added chemicals. and this is funded by a £60 million Innovate UK Energy Research Accelerator.
Being part of the Energy Research Accelerator and having located here at Tyseley Energy Park, we have now the right setup to deliver the thermal belt for Birmingham, including 15 to 20 units of TCR technology, taking residue material from all over the place and delivering green hydrogen, green fuel and green power to the city.
Okay, so thermo-catalytic reforming. This is a new cutting-edge technology of converting biomass and other waste products to sustainable fuels. So the process involves feeding the feedstock into the TCR reactor, and it's met with a screw reactor where it's then grounded up and heated in the absence of oxygen. So this process is pyrolysis, and it creates the biochar, the hydrogen-rich synthesis gas, and this crude liquid bio-oil. So these byproducts are then fed into a second chamber where it's then catalytically reformed to create a higher quality fuel. So the crude liquid bio-oil has similar properties to crude fossil oil. So you can kind of think of it as like a meat-free substitute of crude oil. And these aromatics can then be further treated to replace the sulfur, nitrogen, and oxygen atoms with hydrogen atoms, therefore increasing the energy content of the fuel. And then they can also be fractionated off into its biopetrol, biodiesel, and biokerosene fractionates. So the biodiesel specifically conforms with standard EN 590, which is the standard used for conventional fossil diesel and road vehicles. And again, it gives the requirements and the test methods on what properties the fuel needs to have for it to be used in a diesel engine. And then lastly, this biodiesel can also blend with other biodiesels and fossil diesel as well. So comparing the two biodiesels, they have their similarities and their differences. So their energy content is similar to fossil diesel. They can be blended with each other or fossil diesel. Pure biodiesel can be used in diesel engines without any engine modifications, and both of them can be hydrotreated to improve the fuel quality. And then the differences I've explained here. More notable difference is the different hydrocarbons that you get, depending on what process you use. So because these methyl esters depend on the fatty acid content, it can give rise to oxidation stability problems, having a lower energy content, but on the upside being having a higher completed combustion. And then the opposite being true for the TCR biodiesel. So my project aims to answer the following questions. What limitations arise when using hemp biomass as a source for biodiesel? Does the hemp-derived HTCR biodiesel adhere to standards set by EN 590? Are there any additives that are necessary to achieve this standard? And then I want to look at the engine performance of 100% fossil diesel for baseline data, and then increasing the blend of HTCR biodiesel in the following increments. I'll then conduct separate repeated tests of 80% HTCR biodiesel and 20% hydrogenated fatty acid methyl ester biodiesel. And I'll explain later why this mixture I find more significant. And then I want to look at how economically viable it is to upscale this process and create both biodiesels so that it can fully replace fossil diesel as well. So stage one of the project will be completed through my master's final year project. So it'll be computational modeling of the fuels in an engine simulator. So I'll have to get the biomass and convert it into the bio-oils. I'll be producing lab scale test samples, so about 1 liter in total. I'll then test critical biodiesel properties with the EN test standards. And these are the properties that I'll be analyzing for the time being. Then I'll determine the composition of what hydrocarbons are present within each fuel using gas chromatography and mass spectrometry. And then I will determine the composition of what elements are within each fuel using ultimate analysis. So this data will then be used to simulate these fuels in an engine simulator, and I hope to obtain theoretical data which will give me an indication on the fuel quality within combustion. So then that moves on to stage 2, which is again producing and analyzing the fuel quality. The more notable difference is that in this stage, I'll probably need about 20 litres of biodiesel, which will then be used for the third stage, which is the practical engine tests. But this will involve converting the biomass into the bio-oil, and these conditions are listed here. And then hydrotreating the bio-oil using these reactants, catalysts, and then these conditions as well. Then fractionating off the biodiesel and testing it with these analytics. Another difference in this stage is this EN test standard. So in stage 1, I was only testing the critical properties, which I think will be needed for computational modeling. But in this stage, I want to test the EN standard in full and get the full raw data and make sure that it's EN 590 certified. I'll then do the same process with hemp seed oil into the hydrogenated fatty acid methyl ester. So hemp seed oil is a commercially available product, easy to get hold of. The process I'll be using is a one-pot transesterification and selective hydrogenation process. So it's doing both transesterification and selective hydrogenation in the same reaction. This is for both convenience and also the high product yield that this study produced. And then again, I'll be testing it in accordance with these analytics, the EN standard, gas chromatography, mass spectrometry, and ultimate analysis. So these last steps, the analytics, will then be used to determine the fuel quality of both biodiesels. If they show to be of high quality, then it can move to its third stage, which is the practical engine combustion tests. So like I said before, it'll be combustion of the following mixtures, going from pure fossil diesel to pure HTCR biodiesel, and then using 80% HTCR biodiesel and 20% hemp seed biodiesel. So this mixture I find quite significant because I've included 20% methyl ester because I want to promote cleaner combustion. However, I don't want to put too much methyl ester that it compromises in the lower energy content. And then finally, I'll be analyzing the engine, these engine parameters to measure the engine performance. So during my research, I came to the realization that hemp would be a really sustainable replacement for a variety of different products. So my next question, and maybe you're wondering as well, is why is it not used everywhere? Well, cannabis has a long history within the UK. Dating back to 1533, King Henry VIII actually mandated that landowners grow a quarter acre of hemp for every 60 acres that they own. Then later in 1579, Queen Elizabeth I increased these quotas to 1 acre and even went further to impose a fine of £5 for landowners who failed to comply with this quota. Then during the 16th to 18th century, the British Royal Navy grew to be one of the most powerful navies in the world. And this was because of their sailing navy. So the sailing navy used hemp sails and hemp ropes within the design. But then in the mid to late 19th century, there was the decline of the sailing navy, and this was replaced with steam-propelled ships. And as a result, hemp cultivation decreased. Then in 1928, the Dangerous Drug Act included cannabis and its other raw forms to the act, and therefore cultivation became illegal. This isn't in the UK, but in 1941, Henry Ford produced a car door and fender prototype from hemp-based plastic. So he envisioned that the entire chassis of this car would be made from this hemp-based plastic, and the car would also run on hemp ethanol. Then in 1971, the Misuse of Drugs Act classified cannabis flower, resin, and oil as a Class B drug. But then in 1993, the Home Office granted licenses to grow hemp for its industrial applications, but they imposed regulations surrounding the cultivation. So as it stands, to cultivate hemp, you can only cultivate it for its stalk and seeds, as these are non-controlled parts of the plant. You need a license from the Drugs and Firearms Licensing Unit of the Home Office. You have to undergo a DBS check to be eligible and pay a fee of £580 for the first 3 years, and then £326 each growing season afterwards to renew it. The leaves and flowers cannot be harvested with this license because they're controlled parts, but you can be licensed to cultivate high THC cannabis or the controlled parts with a more expensive license. If you are granted a license, you then may be subjected to a compliance visit, And if one is needed, you need to pay a fee of £1,371 for this to be arranged. Now, the flowers and leaves have to have a THC content of less than 0.2%. And this is quite a restricted limit because while the THC concentrations are mostly determined by the strain or what genotype of cannabis you're using, so seed suppliers will tell you the range of THC that a particular seed will give you. And while there are 0.1% seeds, the problem then comes when you actually come to grow the seed. So climatic conditions can affect the THC content. And if a seed says it's 0.1%, you may find with optimal climatic conditions that you may get plants that have 0.4, 0.5% THC, and these would be illegal plants and therefore have to be destroyed. But then there's actually a positive correlation between THC content and seed and fiber production. So it's actually more beneficial to use higher THC concentration plants if you're using it for industrial applications. So because of the stigma surrounding cannabis and also the added cultivation restrictions and costs, this isn't a very publicly favored crop to use. And there's no infrastructure there's not much infrastructure in place for hemp processing to process it into its byproducts. Therefore, there's quite a high startup cost because you need quite advanced machinery to process it. So what can we do about current regulation? Well, we need to put pressure on Boris Johnson and his government to remove the barriers and U-turn their stance on cannabis prohibition. So the current legal cases that are forming against the government now are with We the Undersigned on cannabis prohibition and also Plan B on their environmental policies as well. So We the Undersigned believe that the Home Office has provided disinformation on cannabis. The government stance is that cannabis is a harmful drug and can damage people's mental and physical health and harm individuals and communities. But there's actual substantial evidence that shows that cannabis can be used to treat chronic pain, anti-emics for chemotherapy-induced nausea and vomiting, improving MS spasticity symptoms, and epilepsy as well. And this is because of how cannabinoids actually affect our endocannabinoid system. And so We the Undersigned also believe that the Home Office have been denying cannabis consumers their human rights, those being freedom of thought and consciousness, respecting a peaceful private and family life, and being free from interference by public authority. So a real example of what We the Undersigned are fighting for, there's a man in Cornwall. His name is Philip Bevington. Now, he's 80 years old with severe and terminal stage 3 kidney failure. And he was visited the police on 2 occasions for the cultivation of 24 cannabis plants he had in November 2019, another 24 that he had in January 2020, and 21 cuttings. But when discovered, these cuttings were not actually controlled parts. Now, the police are charging him for the cultivation and production of 70 cannabis plants, and the production charge ties him into crime, but he uses cannabis to alleviate the pain and other symptoms of his illness. Now, whatever your stance on drugs may be, I'd like for you to keep an open mind on what I say next. So NICE, the National Institution of Health and Care Excellence, they provide guidelines for the NHS to prescribe certain drugs, one of them being cannabis as well. So they've imposed very strict guidelines on how the NHS can prescribe cannabis use for the things I mentioned previously. And because of these strict guidelines, it actually makes the NHS, makes it impossible for the NHS to prescribe cannabis. So the only real viable way of getting a prescription for cannabis is through clinical trials or private clinics. But these private clinics have high cost of access and there's no guarantee of a prescription. So Mr. Bevington, when faced with these options, he felt that he would only cultivate for personal use. And it really shouldn't be a question of whether Mr. Bevington was right or wrong to cultivate for personal use. It should be whether the police were justified to invade this man's private home when he imposed no threat to his community or to himself. It was his choice to grow for his personal use, and therefore he should be free from the interference of public authority. So we, the Undersigned, basically are trying to fight the injustice that the Misuse of Drugs Act has caused since when it's been implemented. And it raises the question if enforcing the Misuse of Drugs Act is actually a suitable allocation of taxpayer money, because it costs the Home Office £10.7 billion a year to enforce the Misuse of Drugs Act, whereas it costs the NHS £500 million a year to treat drug misuse. And then moving on to Plan B. Plan B are challenging the government on their environmental policy. So before 2019, the 2050 carbon target was reducing emissions by 80%. So Plan B felt that this was not sufficient enough, and the government needed a more coherent plan. This was an unsuccessful claim in court. However, the government later reviewed their targets to be net zero by 2050. They then challenged the government on the Heathrow expansion, and this was a successful claim. The Heathrow expansion was deemed unlawful, and now they're trying to challenge the government on their bailout for polluters. So the government have allocated £1.8 billion to airline companies, but failed to consider their climate obligations as well. So it's quite contradictory that when the government was presented an opportunity to get these airline companies on board with their net zero targets, they completely missed out. So now moving on to the local case study. So the Tyseley Energy Park are investing in a 4-phase master plan to develop their site. Phase 2 of the plan being to provide the UK's first low carbon refueling station. And this will have infrastructure in place for hydrogen, electric and biodiesel refueling. So depending on the outcome of this research, this fuel could be used within this station. And then the Birmingham City Council are imposing a clean air zone within the city centre. So this is to improve the air quality by incurring charges on the most polluting vehicles from entering the city centre. But really what this scheme should be trying to do is incentivise the switch to 100% biodiesel, as these fuels have a minimal environmental impact as a closed loop carbon cycle is created. And then there's also the wider implications to other clean air zone schemes within the UK as well. So then just some concluding remarks is that it's essential for the UK government to achieve its net zero targets as soon as possible. The supply of diesel could be affected post-Brexit transition in the event of a no-deal Brexit. Industrial hemp has promising qualities to be integrated within climate and energy policy, but this is really dependent on if the public put pressure on the government to remove the regulations surrounding hemp cultivation and make it more viable. More research is needed on the combustion performance of HTCR biodiesel and also the other fractionates in automotive and aviation engines, as really this TCR technology has promising benefits for the environment. So the overall time frame for this project is 24 months with a cost of £256,000. So that's the end of my presentation. Thank you for listening. Are there any questions?
Oh, thank you. Yeah, can you hear me? Hello.
Yeah.
Yeah, thank you, Michael. Thank you for your wonderful presentation. Dear attendee, if you have any question, please raise your hand or type in the chat box. Hi, Michael. I want to ask some questions first.
Okay.
We can wait for other attendees' question. Yeah, the first one. In your slide, I saw that you compare the FAME biodiesel and the TCR biodiesel. Have you measured of their composition? Of these two types of biodiesel? Because we know that the fuel composition will finally determine the fuel properties. Therefore, I want to know something about that. Thank you.
With the methyl ester, so I have read some studies, and there are studies out there that show the typical composition of what fatty acids are within hemp seed oil. There's also been a study that shows the composition of what hydrocarbons are with the TCR bio oil. The only problem with the bio oil one is that it's for the crude general bio oil. So I'm not sure from those hydrocarbons which ones specifically are then refined to be biodiesel, which one then goes to biopetrol, and which one goes to biokerosene. but like I said, there are studies out there for the composition of hemp seed fatty acid methyl ester. I'll include this more in my report, but for the presentation, I didn't want to go too deep into what the compositions were.
Yeah, thank you, Michael. Yeah, we received a new question. I unmute Lisa Jaber. Hello, Lisa.
Yes, hi.
Yeah,
well, I did
yeah.
type my question, but I'm happy to read it. Yeah, so thank you, Michael, for the presentation. It's very interesting. Do you know, or do you think that adopting this biofuel is under consideration or would be under consideration in countries or places where they have more relaxed restrictions regarding the cultivation of hemp? For example, California or many other countries now are relaxing these restrictions. So do you feel this is something that they might be considering, or are they starting to consider it?
Okay. So I think the benefit with this TCR technology is because of the wide range of feedstocks that it accepts. So in the UK, it may not be viable to solely dedicate hemp cultivation for biofuels application. But the added benefit of TCR is that it can accept a range of different feedstocks. So you can actually, so if a company were to set up that solely dedicated to using TCR, they could contact a range of different companies and say, just give me your waste for free, and we will come collect it, or however it's arranged for it to be collected. Then they have a low cost of feedstock, which then also compromises with maybe the higher capital cost of actually setting up the TCR technology. So that also ties into the previous question in Herrera's slide about the cost of biofuels as well, is that this TCR technology may actually prove to give cheaper biofuels as a result of the wide range of feedstocks that it can accept. I hope that answered your question.
Thank you.
Oh, thank you, Michael. Yeah, I have one more question. We already know that some industry they also adopt the catalytic reforming technology to convert the biomass and gasification the biomass into the fuel into the gas fuel, like the syngas or the liquid fuel. What is the difference between your technology? What is the innovation of the TCR technology compared to the traditional technology? Thank you.
So there's different methods of converting biomass into sustainable fuels. So there's gasification, and then there's pyrolysis as well. And then you can also do like fermentation as well. So this TCR technology, from what I've gathered from the research that I've looked at, it's nothing particularly innovative, more in the sense that it just combines these two different processes together to form one process. So it still uses the fundamental knowledge of these previous conversion processes, but then it just combines them into one system.
Thank you, Michael. Yeah. And one more question. Do you know what exactly happening in the reactor of the which conducting the catalytic reforming? Have you investigated what's happening inside? Any
so I was actually
pathway?
worried if someone would ask this question. So from the papers that I've read so far, they've kind of said that they do the intermediate pyrolysis, and it degrades the biomass by heating it with the absence of oxygen. And then kind of the next sentence is, oh, it's then catalytically reformed to improve the fuel quality. So chemically, I'm still unsure as to how it actually converts it into a higher quality fuel. But that's like probably when I start my project in more detail, I'll have more conversations with professors and postgraduates on what's involved chemically with this catalytic process.
Okay, thank you, Michael. Yeah, our attendees, do you have any more questions to Michael? Please raise your hand. Michael, if